thank you for the opportunity to show our options, our possibilities in the field of surface metrology, optical properties. Excuse me. Okay, so the laser pointer maybe does not work. What I will show is optical properties, and thin film metrology means thickness characterization of thin films. And I'm coming from the company Park Systems. Park Systems is a company from South Korea and is doing atomic force microscopy. And since a little bit more than 1 year, a Korean is part of Park Systems. So what we can offer from the point of view of Park Systems is atomic force microscopy and imaging ellipsometry. And I was asked, how long are you doing this? So atomic force microscopy, Park System is doing from the beginning. And imaging ellipsometry, we do from the beginning. So both companies are really directly related to the starting of these technologies to characterize surfaces. But in this talk, I will focus on imaging spectroscopic ellipsometry. And yeah, first I will start with an introduction. You see the setup. If you want to see more of the setup, you can just look behind the presentation part. There's the complete system. This is part of our assignment. And yeah, what is imaging ellipsometry? So maybe you are familiar with ellipsometry, characterizing thin films. You get a number, the number of thickness of your layer. We combined imaging ellipsometry with a microscope. So we have a microscope optic in the system so that we get not the number of the thickness, we get an image of the thickness, a microscopic map, or we get an image of the ellipsometric parameters, and you select the area where you want to have the thickness, and then you get your number. So this is what we are doing. So it is a non-contact technique to characterize thin films, pattern thin films, structured thin films. It measures film thickness and all optical properties. That is, of course, you cannot have everything with one wavelength, for example. So that is really the question what you need and what is required from the point of view of the technology. And at the end of the day, we end up with such a system or such a system you can see behind. And then typical applications is the characterization of 2D materials. We have a unique pattern method to measure ellipsometry on curved surfaces. Most people would say, well, it doesn't work. Yeah, it works with a special application of imaging Müller matrix ellipsometry. We have a unique tool for transparent substrates. We call it a beam cutter, so that we get rid of the backside reflection, a typical problem in ellipsometry. So we have a simple technique to get rid of it. We have application surface engineering. For us, atomic layer deposition is one of these types of applications in the field of surface engineering. We have photonics, where you can measure the optical properties of a waveguide, even if it's just getting a microscopic waveguide. We come from the award interface. So the origin of the company was boosting a microscopy in a language logic film. So this is still possible. We can characterize anisotropic films with Müller matrix application or with imaging Müller matrix, biointerfaces, MEMS, everything where you want to get ideas regarding structure, regarding film thickness on very tiny areas. How does it work? It is an ellipsometer, so we have a light source. We have a polarization generation part with a polarizer and a compensator or a automatic lambda quarter plate, just how you would like to prefer the naming. We have our sample, and then what other ellipsometer not have in this way, we have the objective lens and a camera. Our detector is a camera, so we are recording always images of the surface, and that has an influence on the way how we treat, for example, microscopic things. We come with parallel light to the surface. We don't need to microfocus, what is, of course, producing some uncertainty regarding the angle of incidence. And we select on the detector side where we want to do the measurement. And the benefit is that we can go down to a resolution of 1 micrometer with ellipsometry. The benefit is that we have, depending on the camera, around about 300,000 points, values for our data. So each pixel is more or less a single ellipsometer. And we have not our eyes wide if we're talking about microfocusing, if we're talking about tiny surfaces, tiny areas. So what we are doing, we record images by changing the optical components. And out of these different images, out of the grayscale distribution, we calculate, for example, phi and delta, or if we talk about Müller matrix, the different elements of the Müller matrix. So everything is based on the images that are recorded when we change the state of polarization. And ellipsometry is an indirect method. So we have our values, delta psi, we have our optical model, and we have a fit engine, that's the powerful fit engine we have, and then we get, for example, a thickness map or other type of data. So what does it mean, optical model? Optical model means that we need to know the optical properties of each of these layers. Or we need to know the thickness of each of this layer and can calculate the optical properties. Or we have enough data that we can independently calculate things. So we have a set of variable parameters, and we can measure a number of parameters to describe the set. And depending on how many parameters we can measure, it's of course depending what we can really, how many parameters we can get out of this system. Okay, so this was how it works. Now I come to the typical, we call it methods. So first of all, it is also a microscope. We get images of our surface. Depending on the state of polarization we have used on both sides of the sample, we can tune the contrast and the quality, the contrast between different parts of the surface. We can go to the so-called nulling condition, so no reflectivity from the substrate, and increase the contrast for thin films. Or we can do the opposite. So we can really play with the optical contrast to get the first impression of the image. And the first impression means that we, for example, in case of graphene, see steps of atomic layers. So it's atomic resolved method for this type of application. And the next step is that we measure the ellipsometric angles delta and psi, and we measure them based on these images. So we get microscopic maps of delta and psi, and can calculate, if we know all the optical properties, thickness maps. I think that is maybe the working horse of imaging ellipsometry. The next step is that we do the same, measuring delta and psi, but for example, in this case, for different wavelengths between 360 and 1000 nanometers. So you see, every slightly change here is one map. And we can measure all these maps, and we can then use some statistical methods to find parts that are identical, or we can just select an area and make it, we call it pixel shot, to calculate the spectra. So we can do spectroscopic measurements, and as I mentioned, if you want to have more variables, you have to measure more parameters. So that is one opportunity. The next step is that you measure delta and psi at different angles of incidence. Of course, that is a very helpful tool to decouple the optical properties from the thickness. That's the reason why variable angle spectroscopic ellipsometry is a standard method, and imaging variable spectroscopic ellipsometry, of course, combine these things. And I should mention that we have a new method to do the measurement that increases speed dramatically, so that we really get these type of measurements in periods of minutes and not something like an hour or hours. And that, of course, is quite helpful. So now I run back. Here I was still talking always about microscopic maps. So now, if you want to have something similar to a normal ellipsometer, just the numbers, we can use our so-called regions of interest concept. So we can select in the image different parts where we would like to have the results later. So you just get then the normal data for an ellipsometer, but for these areas. And you can also add, if you have such a pattern, a number of different areas, measure the in parallel, so in the same measurement, you get the data, the spectra for these different areas, and then you can put it to the model and do the characterization regarding thickness and or optical properties. And of course, you can go even one step further, make such a pattern so that you get then, how to say, the complete spectral pattern of this is, for example, for this line. So you can go even to the next steps and to increase the number of data. And yes, the next point, and you saw some of these images. I think maybe you realized it, that you saw it yesterday in the first talk. We saw a number of images of these stitched images, and even yesterday, Ivan showed me a number of very nice stitches. So I think stitching is here the working horse of the imaging ellipsometer. How long?
5 minutes.
5 minutes. Oh, then I have to speed up. Okay, you can put all these images together, delta phi map, and you have the microscopic resolution. And now I come to the topic of my talk. Characterizing ALD printed structures, but I just will repeat the same, but on these type of structures. So what ATLANT is doing, they print these structures, lines, whatever you want. And we did delta psi maps. We, of course, wanted to measure the thickness, so we needed to develop our optical model. And I have always mentioned which instrument is, how to say, useful for this type of application. So we characterize spectroscopic measurements of these stripes. So here are the sets of maps we have measured. Then I selected different regions of interest. I wanted to see if it is, how to say, the size has an influence on the optical properties. Are they homogeneous? So I selected different size regions of interest, and then did the optical modeling. So here you see the result for the different areas of the sample, and then the fitting result for the starting material, the basic material. I assume that the basic material is always the same, and our software can handle these different samples together and making one general model out of these things. So I get, of course, the fitting results of the optical properties and the thickness of the different areas. We did the same with the stitching. So we recorded all these microscopic maps, stitched them together, and calculated the thickness map based on the model we have characterized before. And yeah, this was the thickness part. And then maybe some things that could come next. Transparent substrate. We have mentioned that we have our so-called knife edge illumination or beam cutter to get rid of the backside reflection to measure on transparent substrates. So you see it's just a tool that can be moved down in the instrument. Here you see the effect. This is done with this stitching with the beam cutter. That is done without the beam cutter. And yeah, this is the complete spectra. Here you see this part is where the shadow is from the beam cutter. This is without the beam cutter, where you see all the oscillations of the materials. So this is a silicon carbide sample, mainly H4, 4H, and these are the spectra. So the spectra with the beam cutter, like a normal substrate, and the spectra of the sample without the beam cutter. 2D materials, as I mentioned, 2D materials are characterized frequently. This is a very nice paper from the Harriet Watt University in Scotland, and they characterized, and together with Sheffield University, I should say, they characterized a number of 2D materials, and what they did, they measured the thickness with an AFM, and in the second step, they used the ellipsometer to characterize or to calculate the optical properties for these very thin films. And operando imaging ellipsometry, so we characterized together with the University of Göteborg graphene, Janus graphene, where you could intercalate sodium ions, and we followed for 8 layers of graphene the battery process. It was maybe one of the smaller batteries of the world. It was only an 8-layer graphene battery, but we could nicely see the change of delta psi when we are charging and decharging the battery. And also when we take different images, we could also see nicely where in the flake the activity is high and where not. So that was the operandum. This is just more, I don't see any application, but I really love this image changing from Van Gogh to someone else. And yeah, maybe other locations. I think you always related to other space galaxies. And yeah, any questions?